300 horsepower. That's what separates winning from watching in top fuel drag racing. And in 1992, one Louisiana mechanic found that power hiding in the most unlikely place imaginable: the teeth of a pulley. Dale Armstrong didn't just bend the rules. He exploited a blind spot so obvious, so embarrassingly simple, that when competitors finally discovered it, they couldn't believe they'd missed it for nearly 6 months. This is Motorsport Heritage, and I spend way too much time thinking about the engineering secrets buried inside drag racing history. If you're someone who loves uncovering the clever, hidden innovations that changed motorsport forever, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. Now picture this. It's summer 1992 at a drag strip in Texas. The air is thick with nitromethane fumes that burn your eyes and coat the back of your throat. 2 top fuel dragsters line up at the starting line. 8,000 horsepower machines that can accelerate from 0 to 330 miles per hour in under 4 seconds. The Christmas tree lights drop. Yellow, 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 green. Both cars launch with a violence that hits you physically in the chest from a quarter mile away. But something is different about one of them. The engine note is higher, angrier, like it's screaming at a frequency that shouldn't be physically possible. That car crosses the finish line 3 car length ahead, and afterward, in the pits, crew chiefs crowd around the winning engine trying to figure out what just happened. They check the blower, standard 1471 unit. They examine the fuel system, nothing unusual. The camshaft, the headers, the clutch, everything looks completely regulation. But somewhere in that aluminum maze of precision parts, Dale Armstrong has hidden an advantage worth 300 horsepower, and it's sitting right there in plain sight. This is the story of how a mechanic from Louisiana outsmarted the entire NHRA rulebook with a modification so simple, so elegant, that it almost seems insulting to the complexity of everything surrounding it. Armstrong didn't invent a new supercharger or discover some exotic fuel additive. He solved a problem that every top fuel team in America was struggling with, and he did it by borrowing technology from industrial conveyor belts. Let that sink in for a second. Conveyor belts. To understand Armstrong's breakthrough, we need to understand the brutal physics of top fuel drag racing in the early 1990s. Look, these weren't just fast cars. They were controlled explosions on wheels, burning through 15 gallons of nitromethane in a single quarter-mile pass. The engines operated at the absolute edge of mechanical possibility. Connecting rods stretched like taffy under load. Cylinder heads lifted off the block despite being held down by bolts torqued to 190 pound-feet. Spark plugs literally melted into glowing embers after a single run. And according to data published by NHRA technical officials in that era, a top fuel engine would consume and destroy more mechanical components in one 4-second pass than most street engines see in an entire year of operation. At the heart of these monsters was the supercharger, specifically a Roots-type blower that could move 900 cubic feet of air per minute. Now here's what most people don't realize about these blowers. They weren't the polite superchargers you'd find bolted to a street muscle car. A top fuel blower consumed 900 horsepower just to turn it. Think about that for a moment. The blower alone required more power than an entire NASCAR Cup engine produced. But it was absolutely worth it, because that blower could cram enough air into the engine to support combustion of nitromethane at rates that would have seemed like pure science fiction just a decade earlier. Here's where Armstrong spotted the problem that everyone else had accepted as inevitable. The supercharger was driven by a reinforced rubber belt, essentially a giant timing belt on steroids. As teams pushed for more power through the late 1980s and into the early 1990s, they kept spinning the blowers faster and faster. More blower speed meant more air. More air meant more fuel. More fuel meant more power. Simple equation. Except for one critical thing. The belt couldn't keep up. At 8,000 revolutions per minute blower speed, the belt was traveling at over 150 feet per second. The acceleration forces were so extreme that the belt would actually slip on the pulleys. Not dramatically, we're talking about microseconds of slip that you couldn't detect with the naked eye. But those microseconds added up brutally. Testing data from that period showed that at maximum load, the driven pulley, the one bolted directly to the supercharger, was actually turning 10 to 12% slower than it should have been based on the theoretical drive ratio. That slip was costing teams somewhere between 300 and 400 horsepower. Gone. Wasted as heat and friction. Now, you might be thinking, surely somebody would have fixed this, right? The NHRA had some of the most obsessive engineers in American motorsport working on these cars. And you'd be right. Everyone knew about the slip. It was just accepted as one of those unsolvable facts of life in top fuel racing. Teams tried everything. They experimented with different belt compounds sourced from rubber manufacturers across the country. They increased belt tension to the point where the added load started cracking crankshaft snouts. Some teams even tried running multiple belts in parallel, but the packaging constraints of the engine compartment made that completely impractical. The consensus across the entire paddock by 1991 was that approximately 2,200 horsepower was roughly the ceiling, the maximum you could reliably extract before belt slip became the hard, limiting factor. That number wasn't a target anymore, it was a wall. And that's exactly what made Armstrong's solution so brilliant. He didn't try to fix the belt. He fixed the pulley. Here's the thing about Armstrong's background that made all the difference. Before he entered racing, he'd worked in industrial automation, designing conveyor systems for manufacturing plants across the American South. In that world, factory floors where production lines ran 24 hours a day, timing and synchronization weren't just performance concerns. They were existential ones. A conveyor belt that slipped even fractionally could throw off an entire production line, costing thousands of dollars per minute in downtime. So industrial engineers had spent decades developing highly specialized tooth profiles for timing belt pulleys, profiles engineered specifically to provide maximum grip under sustained load without causing excessive belt wear. These weren't the rounded, smooth-bottomed automotive-style teeth that racing teams were using. They were precisely machined profiles with specific pressure angles and carefully calculated root radiuses designed to mesh perfectly with the belt's tooth geometry under dynamic load conditions. And crucially, nobody in drag racing had ever thought to look at them. Because why would they? Racing engineers looked at racing solutions. Armstrong looked at everything. One night in his machine shop in Louisiana, Armstrong was sitting at his workbench staring at a worn supercharger pulley, running his fingers slowly over the polished teeth where the belt had been slipping repeatedly. The aluminum was actually glazed, burnished smooth from the repeated friction cycles. And that's when the connection hit him like a thunderbolt. Why were they using automotive pulley profiles for an application that had far more in common with an industrial conveyor system than with any car engine ever built? He pulled his machinery's handbook off the shelf, the Bible of mechanical engineering that sits in every serious machinist shop, and started looking up specifications for industrial timing pulleys. What he found would change top fuel drag racing forever. The standard automotive pulley tooth profile used across drag racing had a 20-degree pressure angle with relatively shallow tooth depth. It was designed for smooth engagement, quiet operation, and long service life under moderate loads. Perfect for a street car. Absolutely terrible for transmitting 900 horsepower through a rubber belt at 150 feet per second. Industrial timing pulleys, by contrast, typically used a 14-degree pressure angle with significantly deeper tooth engagement. The difference in numbers might not sound dramatic, but it fundamentally changed the geometry of how the belt wrapped and gripped the pulley under load. With a 20-degree angle, the belt teeth tended to ride up and out of the pulley groove when load peaked. With a shallower 14-degree angle and deeper tooth engagement, the belt locked itself more securely into the pulley the harder it was pulled. Armstrong didn't simply copy an industrial design wholesale. That would have been both too obvious and insufficiently optimized for the specific conditions of drag racing. He needed something tuned precisely to the loads, temperatures, and rotational speeds of a top fuel application. So he spent 3 months in his machine shop cutting different tooth profiles on his lathe and testing each iteration on a dyno. He methodically worked through different pressure angles, 12 degrees, 13, 16 combinations of depth and root radius that had never been tried on a drag racing pulley before. Every prototype got a number. Every test result went into a dedicated notebook with detailed measurements of belt surface temperature, slippage percentage, and calculated power transmission efficiency. This wasn't guesswork. It was disciplined, systematic engineering conducted in a small Louisiana machine shop by a man who understood both the theory and the craft. The breakthrough came with prototype number 23. Armstrong had combined a 14.5-degree pressure angle with a tooth depth that was 15% greater than the standard drag racing specification, paired with a root radius profile that matched the belt's own tooth geometry under dynamic load, not static load, which is what most pulley manufacturers design for, but the actual deformed shape the belt tooth took when it was being pulled at race conditions. When he put prototype 23 on the dyno, the belt surface temperature dropped by 40 degrees Fahrenheit compared to the standard pulley. That temperature drop told Armstrong everything he needed to know. Less heat meant less energy being wasted as friction. Less friction meant less slip. Less slip meant more of the engine's power actually reaching the supercharger rotors. The dyno confirmed it quantitatively. The supercharger was now spinning within 2% of its theoretical drive ratio speed. He had eliminated approximately 90% of the belt slip that the entire sport had accepted as unavoidable. But here is where Armstrong's genius really showed beyond the engineering. He didn't just make one custom pulley. He manufactured a matched set. Both the drive pulley on the crankshaft and the driven pulley on the supercharger, with precisely matched tooth profiles. And through additional testing, he discovered something else that nobody had anticipated. The rotational timing of the two pulleys relative to each other was critical. The pulleys needed to be clocked so that the belt teeth engaged both pulleys at exactly the correct phase relationship. Get it wrong by even a single tooth position, and the meshing geometry actually created localized stress peaks that made slippage worse. Get it right, and the belt locked onto those pulleys with a grip that felt almost mechanical rather than frictional. The first track test was conducted quietly at a private test session in early 1992. Armstrong installed his custom pulley set on Kenny Bernstein's top fuel car, the same car that had recently become the first in history to officially break 300 miles per hour. With the standard pulleys in place, the engine was producing 2,280 horsepower on the team's in-house dyno. With Armstrong's pulleys installed, same belt, same blower, same fuel system, same everything else, it produced 2,510 horsepower. The increase was so immediate and so large that Bernstein's crew chief assumed the dyno was malfunctioning. They recalibrated the load cells 3 separate times. The numbers held every time. Making power on a dyno is one thing. Translating it to the racetrack is another problem entirely. The first full competition pass with Armstrong's pulleys nearly ended in disaster. The engine was producing so much power that it completely overwhelmed the clutch engagement program that the team had spent 2 seasons carefully developing for 2,200 horsepower. The car hazed the tires through almost the entire first half of the track, something that hadn't happened to that team in over 2 years of racing. They had to completely rebuild their clutch management calibration from scratch to accommodate the additional power the engine was now actually delivering to the drivetrain. It took 6 more test passes, each one providing data, before they found a clutch setup that could put the new power level effectively on the racing surface. When they finally got it sorted, the advantage on the track was devastating. At the 1992 NHRA Summer Nationals, Bernstein's car was consistently running 2 to 3/100ths of a second quicker in the first half of the track compared to anything else in the field. In top fuel drag racing, where entire races are decided by thousandths of a second, 2/100ths represents an enormous, almost embarrassing margin. Other teams noticed immediately. After each round, crew chiefs would casually drift past Bernstein's pit area, leaning in to study the engine under the guise of casual conversation. They examined the injector nozzles. They studied the blower intake configuration. They stared at the exhaust headers. The pulleys were right there, bolted prominently to the front of the engine in full view of everyone. But they looked normal enough, the same general shape and size as a standard pulley, that nobody gave them a second serious look. Armstrong had also taken careful steps to protect the secret. He had all of the custom pulleys hard anodized in matte black, not unusual for engine components, but the dark finish also obscured the machined tooth surfaces and prevented casual visual inspection of the profile geometry. He ensured that the pulleys were never removed or exposed when competing teams were present in the pit area. If the crew needed to change a belt between rounds, the car went into the transporter first, with the door closed. When rival crew chiefs asked Armstrong, sometimes directly, sometimes through back-channel conversations, about the team's sudden power improvement, he consistently deflected credit toward refinements in the clutch management system and fuel mixture calibration. These were technical half-truths that sent competitors chasing ghosts in the completely wrong direction for months. The NHRA rulebook in 1992 was remarkably detailed and specific about superchargers. It specified the allowable rotor sizes, the case material requirements, the maximum drive ratio limits, even acceptable blower case mounting configurations. But nowhere, not in a single line across dozens of pages of technical regulations, did it mention anything about pulley tooth profiles. As far as the rulebook was concerned, a pulley was simply a pulley. Armstrong hadn't violated a single regulation. He had found a performance loophole that nobody else knew existed, because nobody had thought to look for it in that specific location. For 6 months, Armstrong's pulleys remained completely secret. During that period, Bernstein's team won 7 national events. The performance gap was creating genuine desperation among competitors. Don Garlitz, the legendary Big Daddy himself, personally approached Armstrong at a race and reportedly offered $50,000 for information about what the team was doing differently. Armstrong politely, but firmly declined. John Force's crew chief proposed what he framed as a collaborative technology exchange program, a gentleman's agreement where the two teams would share technical innovations. Armstrong wasn't interested. He understood precisely what he had created, and he had no intention of giving it away before he'd fully exploited every competitive advantage it offered. This secret finally unraveled in the most mundane, almost anticlimactic way possible. At the U.S. Nationals in Indianapolis, the most prestigious event on the NHRA calendar, a photographer from National Dragster magazine was shooting detailed technical photography for a feature article on engine components. He happened to capture Armstrong's pulleys at an angle and in lighting conditions that showed the tooth profile with unusual clarity. When he reviewed the images later that evening, something looked wrong to him. The tooth profile didn't match any automotive pulley specification he'd seen in 15 years of photographing race engines. He showed the photographs to a veteran engine builder who had spent time working in industrial machinery before entering racing. That man took one look at the images and immediately recognized what he was seeing. Within 2 weeks of those photographs circulating, every top fuel team in the country was on the phone with machining shops trying to get custom pulley profiles manufactured. The problem was that nobody outside Armstrong's operation knew the precise specifications. The pressure angle, the exact tooth depth ratio, the root radius profile, all of these variables had to be precisely coordinated to work correctly. Teams that attempted to copy the general concept without fully understanding the underlying engineering often made things measurably worse. One prominent team reportedly experienced such severe belt wear from an incorrectly profiled pulley that their belt would stretch and begin slipping even more aggressively than before after just 2 competition passes, costing them more power than they'd had with the original standard pulley. Armstrong later revealed publicly that his development program had consumed over $30,000 of personal funds, a significant sum for a private individual in 1992. He'd destroyed numerous belts during testing. He'd ruined at least 6 sets of prototype pulleys. He'd also experienced two catastrophic engine failures when early prototype designs had gripped the belt so aggressively that the supercharger momentarily oversped before mechanical failure intervened. One of those explosions embedded shrapnel fragments into his shop wall, fragments that, by his account, were still visible there decades later. But every failure refined his understanding of exactly where the mechanical limits were and what the optimum geometry needed to be. This is where it gets really interesting from a broader historical perspective. Armstrong's pulley innovation didn't just give one team a 6-month advantage. It triggered a complete paradigm shift in how top fuel engineers approached every single component on the car. The revelation was this: if something as apparently mundane as pulley tooth geometry could hide 300 horsepower, what other overlooked details were costing teams performance across the rest of the drivetrain? The mindset across the entire paddock shifted almost overnight, from accepting physical limitations to actively questioning every assumption about every component. Valve spring technology advanced dramatically as engineers realized that spring harmonic resonances were costing them usable RPM range. Connecting rod cross-section designs were revolutionized when research determined that aerodynamic drag on the rod bodies inside the crankcase was consuming approximately 50 horsepower at 8,000 revolutions per minute, a loss nobody had previously bothered to calculate. Even intake runner geometry and collector merge angles received the kind of scientific scrutiny that had previously been reserved only for the most obvious power-producing components. By 1993, the NHRA had updated its technical regulations to include specific parameters for supercharger drive pulley tooth profiles. Importantly, the intent wasn't to ban Armstrong's innovation, that moment had long passed, but to standardize and define the technology so that all competing teams would have access to it on equal regulatory footing. Armstrong's specific competitive advantage evaporated with those rule changes, but his legacy was permanently embedded in the sport's DNA. The horsepower progression that followed was staggering. In 1991, the year before Armstrong's pulleys, the most powerful top fuel engines were reliably producing approximately 2,200 horsepower. By 1994, with optimized pulley profiles integrated across the field and the broader innovation culture that Armstrong's breakthrough had inspired, leading teams were pushing 3,500 horsepower. By the end of that decade, 5,000 horsepower had become essentially the competitive baseline. According to data tracked by NHRA technical officials and reported in National Dragster, today's top fuel engines produce in excess of 11,000 horsepower under optimal conditions, a figure that would have seemed like pure fantasy to engineers in the early 1990s. And you can trace a direct, unbroken line from those modern 11,000 horsepower monsters back to a Louisiana machinist who stared at a worn pulley one night and decided to look at it differently. Armstrong's pulley breakthrough also created a cascading series of mechanical challenges that forced innovation across the entire drivetrain. Once teams could reliably transmit 2,500 horsepower through the belt drive system, previously adequate components immediately revealed themselves as new, limiting factors. Crankshaft designs that had performed flawlessly at 2,200 horsepower began failing at 2,500. Harmonic damper specifications needed complete redesign to control the increased torsional vibration amplitudes. Even oil pump capacity had to be significantly revised, because the increased bearing loads generated by the additional power required substantially higher oil pressure and volume than existing pump designs could deliver. The financial implications were significant and immediate. A set of Armstrong's custom pulleys cost approximately $2,000 to manufacture in 1992, expensive for a component that most people would walk past without a second glance, but essentially trivial compared to the competitive advantage they delivered. Teams running those pulleys could demonstrate measurable performance superiority, which translated directly into stronger sponsorship valuations and higher appearance fees at events. Armstrong himself transitioned during this period into becoming one of the most highly compensated crew chiefs in professional drag racing, eventually moving to Don Prudhomme's operation, where his systematic, analytical approach to engineering continued to produce innovations. His subsequent work involved using acoustic frequency analysis to identify combustion inefficiencies in real time, a story that deserves its own dedicated exploration. Here's what most people don't realize about the broader significance of what Armstrong accomplished. In an era when top fuel teams were collectively spending millions of dollars on exotic aerospace-grade materials, early computational fluid dynamics analysis, and increasingly sophisticated electronic timing systems, the single largest performance gain of that entire competitive period came from a part that cost less to manufacture than a decent set of racing tires. He didn't require a wind tunnel. He didn't need a supercomputer or a team of university-educated aerodynamicists. He needed a thorough understanding of mechanical engineering principles, a disciplined testing methodology, and the intellectual courage to question an assumption that the entire industry had accepted without examination. Armstrong retired from active involvement in professional top fuel racing in 2014, but the pulley technology he pioneered is still spinning on drag strips worldwide today. Modern versions are machined from aerospace specification aluminum alloys and treated with surface coatings that Armstrong would have barely imagined in 1992. But the fundamental tooth geometry, that 14.5-degree pressure angle with deep tooth engagement optimized for maximum grip under dynamic load, remains conceptually consistent with the original design he developed in prototype number 23. It is a remarkable testament to how precisely right he got the engineering on his first successful iteration. In interviews conducted years after his retirement, Armstrong was asked whether he had ever seriously considered filing a patent on the pulley design to protect his investment and commercial interest in the technology. He laughed at the question. By the time any patent application could work its way through the system, he said, every team in racing would have already independently reverse-engineered the concept and be running their own versions anyway. But more importantly, he said the real value of what he'd done was never in the specific dimensions of the pulleys themselves. The value was in the understanding of why those dimensions worked. Once you genuinely understood the physics of why belt slip occurred, what variables governed it, and what geometric changes corrected it, you could apply that same framework of thinking to virtually any mechanical system. Identify the loss. Understand its root cause. Engineer a targeted solution. It sounds disarmingly simple. But as Armstrong demonstrated by being the only person in an entire professional motorsport paddock to actually do it, simple answers to complex problems are often the hardest ones to find. There's something that I find genuinely remarkable about the story when you look at it from the outside. Armstrong's cross-domain experience, the fact that he'd spent years solving timing and synchronization problems in industrial conveyor systems before he ever entered professional motorsport, gave him a conceptual vocabulary that pure racing engineers simply didn't have. He could recognize the belt slip problem as a familiar class of engineering challenge because he'd encountered analogous problems in completely different contexts. The solution space he searched was larger than anyone else in the sport was searching, because his experience base was broader. In a paddock that, by necessity, tended to produce deep specialists with narrow technical focus, his outsider perspective was literally worth 300 horsepower. Today, when top fuel teams are working at a level of sophistication where individual engineers are assigned specifically to search for performance gains measured in single-digit horsepower increments, using real-time telemetry, machine learning analysis of historical run data, and components manufactured to tolerances measured in 10,000ths of an inch, Armstrong's 300 horsepower leap from a pulley profile change seems almost impossible to believe. But it happened. It happened because one man refused to accept that belt slip was an inevitable physical reality. He questioned an assumption that every other engineer in the sport took completely for granted, and in doing so, he permanently changed what was considered achievable. The next time you watch a top fuel car launch off the starting line, that moment of pure, almost offensive violence as 11,000 horsepower tries to compress the physics of acceleration into 4 seconds, remember that some of what you're witnessing traces its direct lineage back to a machine shop in Louisiana, where Dale Armstrong spent his nights cutting metal and measuring teeth and running tests on a dynamometer that most professional racing teams wouldn't have considered worth their time. He didn't just outsmart the NHRA rulebook. He outsmarted an entire industry's collective assumptions about what was physically possible. And he did it with nothing more sophisticated than a different perspective on an old problem. In the end, that's the thing that separates the genuine innovators from the very talented people who surround them. They don't only see what currently is, they see what could be, if you're willing to question what everyone else has stopped questioning. Armstrong looked at a slipping belt and saw wasted potential. He looked at a rulebook and saw unexplored opportunity. He looked at a problem that an entire sport had accepted as permanent and decided to solve it anyway. 300 horsepower, hiding in the teeth of a pulley. Sometimes the biggest breakthroughs really do come from the smallest places. You just have to know where to look, and be willing to actually look there when everyone else has already walked past. What's the most clever piece of motorsport engineering you've ever come across? The kind of innovation that makes you stop and think, how did nobody else see that? Drop it in the comments below. And if you enjoyed this deep dive into the engineering secrets hidden inside drag racing history, subscribe to Motorsport Heritage, because we are absolutely just getting started with these stories.